Okay, let's run the second to last 7-minute summary for this modern physics section, applications of nuclear physics, and then we'll end off with particle physics and cosmology, probably later today. Let's fit this guy to width, remove this. Actually, let me zoom out a bit so it's like kind of easier to see. That's pretty good. All right, I'm just gonna zoom right through it. We got 6 sections: interactions involving neutrons, nuclear fission, nuclear reactors, nuclear fusion, radiation damage, uses of radiation. Very cool. If you can make some kind of like innovations in nuclear reactors, you're gonna win a lot of money. Your parents are gonna be pretty happy. Try that out for fun on the weekend if you have some free time. Set a timer for 7 minutes.
All right, 7 minutes, starting now.
Thank you, madam. Let's just open the timer here so I can kind of see what's happening. We wasting 10 seconds here. 6 minutes, 48 seconds. In this chapter, we study 2 means for deriving energy from nuclear reactions: fission, and there should be fusion here. Anyway, I'm gonna zoom through. Interactions involving neutrons. Let's just look at the equations. I'm interested in the equations here. We got interesting looking equation here, KBT. Okay, neutron capture reaction. We got a chemical reaction here, looks like. Actually, maybe atomic reaction. These are atoms over here. Nuclear fission. Fission occurs when heavy nucleus such as U-235 uranium splits into 2 smaller nuclei. Mass defect, okay. There's this MeV. This is mega electron volts. All right, we're gonna zoom through again. Here's an interesting picture, a nuclear fission event. So we got U-235 before fission. After the event, there are 2 lighter nuclei and 3 neutrons, Kr, Ba, and then a bunch of these like gray things, which maybe electrons, or 3 neutrons, I guess. Okay, neutrons. So we got more kind of interactions here. We got an interesting graph: fission, yield percent, mass number A. Not sure what that is, but we got a quick quiz in the energy released in fusion of uranium-238. Calculate the energy released when 1 kilogram of uranium-235, I said 238 over here, sorry, taking the disintegration energy per event to be Q equals this. Okay, nice little example here. We get an energy at the end. Cool thing to practice for a final exam. Nuclear reactors. We got an interesting picture here where we start with one, these guys split into more, and then we get boom, which actually looks like this is the same as this. So this looks like a runaway reaction. Like you get one of these guys, boom, 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 it explodes into like 6 or 8 of these guys. Each of these guys can split into 8, and you get a bunch of energy from that. We got an interesting picture here, artist's rendition of the world's first nuclear reactor. Wow, this is cool. Because of wartime secrecy, there are few photographs of the complete reactor, which was composed of layers of moderating graphite interspersed with uranium. A self-sustained chain reaction was first achieved on December 2nd, 1942. Word of the success was telephoned immediately to Washington, D.C. with this message: the Italian investigator has landed in the New World and found natives very friendly. The historic event took place in an improvised laboratory in the Raquette Court under the stands of University of Chicago Stagg Field, and the Italian investigator was Enrico Fermi. This is so cool, bro. This sentence right here: the Italian investigator has landed in the New World. So I guess they're talking about this in the New World and found the natives very friendly. This is so eerie, bro. World War II. Anyway, we're gonna zoom through. I could probably read about that for hours. Enrico Fermi, here's the man. Fermi-Dirac distribution. You remember seeing that before? Let's read these bold words: the average number of neutrons from each fission event that causes another fission event. That was weird, but we have 3 minutes, 40 seconds. Let's zoom through a bit more. Interesting picture here. I'm not going to look at that too much. We got another kind of picture: control of the power level, safety and waste disposal. Oh, this is probably very interesting: safety and waste disposal. Read this, do a PhD in this, and you should be set up for a pretty solid career. Nuclear fusion, also do a PhD in this, and you should be chilling if you have some free time. Energy released in fusion, okay, terrestrial fusion reactions. I'm not sure what that means, but we got some little equations here, some Q values. I'm not sure what that means. The fusion of 2 deuterions, and we get an answer over here. Try these problems out if you have some free time. Critical ignition temperature, T-ignit. The temperature for the deuterium-deuterium reaction is 4 times 10 to the 8 Kelvin. Wow, that's hot. For the relationship between, okay, I'm not going to read all that. We got some cool graphs here. Let's see, this graph has MK. This is T. I think this might be temperature on the x-axis. And we got watt per meter cubed, power generated or lost. We got some graphs over here. The green line represents power lost by Bremsstrahlung as the what the hell does that mean? Okay, we're gonna zoom through because we got 2 minutes 20 seconds. Magnetic confinement, dude, this is hype. I love electromagnetism, and this looks so interesting. Like, look at this thing. This literally looks like the Tony Stark reactor right here, the first one here, but they got an American flag on it. Classic Americans. Plasma experiment, magnetic confinement to contain plasma. A toroidal device called a tokamak. Oh, interesting. First developed in Russia, is shown in figure 4.10. 4.10a. 4.10a. Bruh, what the hell is this? It's made by Russians, but they put a picture of it and then they put the American version. There's definitely some kind of like sanction related stuff going on here. We're going to keep zooming through because I got 1 minute 30 seconds. Inside a fusion reactor. Cool. Inertial confinement. Interesting picture. We got some more kind of like chemical related reaction looking pictures. Fusion reactor design. We got another interesting picture. Interesting for engineers, I guess. Advantages of a problem and problems of fusion. Okay. Radiation damage. Okay, I think this is Röntgen. I've heard of this before. This is like the amount of ionizing radiation that produces an electric charge. We got 1 minute left. 1 rad. The number of rads. Okay, I'm not gonna read through all that. Wow, there's a lot of tables here. I don't got the energy to read all that. Uses of radiation. Let's end off. I think here this is the last chapter. Nuclear physics and applications are extremely widespread in manufacturing, medicine, and biology. In this section, we present a few of these applications and underlying theories supporting them. Tracing. Okay. Okay, interesting kind of picture. Medical use of radiation. Material analysis. Neutron activation analysis. I got 27 seconds. Radiation therapy. Brachytherapy. Seeds. Food preservation. Interesting. Radiation is finding increased food preservation because exposure to high levels of radiation can destroy and incapacitate bacteria and mold spores. Very cool. Okay, they got radiation experiment here and the summary, and we finish off with 5 seconds. Let's go. This is actually pretty solid. I like finishing the 7-minute timer in time, or the 7-minute summary, but as you saw, I got like the bare bones of this chapter. Like, I got no information. I didn't look at any equations in depth, but here the summary can help us a little bit. Again, I'm kind of gonna leave this deeply for you guys to research. I'm just gonna see thermal neutron capture event. I remember this in the beginning of the chapter. They give us this like atomic reaction here. NX turns into blah blah blah. Not sure what that is. Excited intermediate nucleus that rapidly emits a photon. So I guess this is related to that nuclear reaction stuff. Nuclear fission occurs when a very small. Okay. Fission fragments. Okay, this is that runaway reaction that I was talking to you about. Do they actually say runaway reaction anywhere? Okay, they don't. The reproduction constant K is the average number of neutrons released from each fission event that causes another event. Fusion reactor. Okay, I'm not going to read all that. In nuclear fusion, 2 light nuclei fuse to form a heavier nucleus, and the energy released, the major obstacle in obtaining the useful energy from the fission, is the large Coulomb repulsive force between the charged nuclei at small separation distances. The temperature required to produce fission is on the order of 10 to the 8 Kelvin. I kind of remember that. I remember 4 times 10 to the 8 Kelvin, or 1 times 10 to the 4 Kelvin. I can't remember. And at this temperature, all matter occurs as a plasma. What a crazy sentence. In a fusion reactor, the plasma temperature must reach the critical ignition temperature. Yeah, I remember this. The T ignition has to be less than T. Okay, so I'm gonna end it off right here. That leaves us with particle physics and cosmology. So we've gone through all these chapters, 7-minute summary. You know, it's not the best, but go through it on your own. Check out my 7-minute summaries. If you watch them multiple times, you should start remembering stuff easier. Hopefully, you know, that's the goal of these videos. And as always, thank you for watching. Peace out. I'll see you guys in the next